you want to write this down? We'll get started. Okay, continue. You got that? Yes? Yes?
Yes.
Okay. So, a couple of small things to have a look at. Another way to state Newton's second law is... Now, before I continue, if you were to look at your notes for when you did Newton's second law, I made you write a little note that said, this is not the exam definition version.
Yeah.
So what we're looking at today is actually the exam definition. Another way to state Newton's second law is F equals delta P over delta T, but we have to explain what that is. Delta P is the change in momentum per unit delta time. And what's momentum? Well, momentum P, does actually anyone know what momentum is? Momentum P?
It's the derivative of...
Yeah.
The opposite of the derivative.
Of what? Nearly. Simplest definition is it's mass times velocity. That is mv. That's momentum. With the units, of course, of kilogram meters per second. Now, just before, well, you can be writing this down. So, for the exam, what you could say is, for Newton's second law, Newton said, now I know I gave it as a formula here. They like it in a sentence form in the exam. So, I want you to look at this formula. Remembering that P is mass times velocity. What's the meaning of delta?
Increasing.
Yeah, or change. Yeah. So can somebody try to put this in sentence form? So Newton's second law says that force equals
Increase change of momentum.
equals the good way saying?
Rate of change of momentum.
Rate of change of momentum.
Per unit.
Yeah.
Rate of change of time.
Oh no, you're close to the first time. I would
Per
personally
unit.
go per unit of time. That's the exam definition of Newton's second law. Force equals the rate of change of momentum per unit of time. That you need. Okay, please make sure you have that definition carefully written down. You will appreciate that for a physics exam, this is a common physics exam question. What is Newton's second law? Classic question. It's right up there with what's the difference between a vector and a scalar. You know, like it's a common exam definition. Not just IFY, but any level. Okay. What you'll also need is the definition of momentum, which is simple. It's the product of mass and velocity.
an example, they give us the measurements.
I think so, yeah. Yeah. You have a formula sheet. They're on it, I believe, yeah. Okay, you got that? Yeah. So before we continue, I want to prove that this really is the same thing as F equals MA. Okay? So let's begin the proof. It's not too long, you can write this down. So we'll have our mass, and there's some force being applied to it, and it starts at U and then it accelerates to V. Okay? So according to Newton, F equals delta P over delta T. Delta P is the momentum at the end minus the momentum at the start over the time at the end minus the time at the start. What's the momentum at the end? That's mv. And what's it at the start? mu. The time at the end is t, and the time at the start is 0. So this is equal to m v minus u over t. But what's v minus u over t? Yeah, this is a. And you can see that as well from the formula v equals u plus at. It means a is v minus u over t. So that's how you can get the last bit done. So it's the same. Yeah?
Yeah.
So, why bother if F equals ma works? Like, why do we have this formula? The reason is it's very convenient to use when the time is small. It's the most common situation to use the new formula is when the time is small, or when we want to calculate the impulse. So, we have a definition now. Does anybody know what impulse is? Is correct, it's Ft, yeah. That's a formula for impulse. Do you know the definition of it? It's the change. Yeah? Oh, no, wait. No. Impulse is the change of momentum. That is, impulse is just the delta P. Yeah, it is, yeah. 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 So let me show you that formula you mentioned, how you can get at it. Since you just mentioned it and it's relevant here. So you have the formula F equals delta P over delta T, but we're calling the delta P, we can also call it impulse, which is I, and delta T is just T minus 0. So another formula for impulse is, as you said, F multiplied by T. So you can use that, or you can use the definition. There's two ways to calculate it. So which do you use? Depends on the information they give you. Obviously, if they give you the force and the time, you can use Ft. If they give you the mass and the velocity, you can use delta P. Yeah? Okay, continue. This is a simple one. I want you to calculate it for me. Straightforward. 1,200 kilogram car crashes into a wall at a speed of 20 and is brought to rest. What was the impulse on the car? Now, I do want you to get the signs right, okay? So, in the picture, we'll have the car going to the right, and we'll say right is positive, okay? So, give this a calculation. Which formula are you using for impulse here? Are you using Ft or delta P? Delta P is a little easier. You could still use Ft, but it's more work. You got an answer? You're thinking about the sign. Is it positive or is it negative? Have you made the decision? Okay. You want to tell me what you think? Going with a negative, yeah. Let's have a look. So, the impulse is delta P, which is mv minus mu. The m, what did we say the m was? 1,200. And the v, what's the v? The v is 0. At the end, that rest. 20, I said? Yeah. So it's a negative 2400. What unit? Now, if you use this formula or this formula, it doesn't matter. So if you look at this, you could say the units are? Yeah, Newton seconds would be fine. But if you use this one, what could you say the units are? Not quite nearly. Kilogram meters per second. Yeah. It's negative, meaning that an impulse was imparted backwards onto the car, bringing the car to rest. Yeah, the impulse is the other way. It's a vector because technically the v and the u in the formula is making it a vector. Yeah? Now, the way I like to think of impulse is the thing that hurts you. So when you're talking about a collision, the thing that matters is the impulse, how your momentum changes. Okay, I'll give you an example.
That's when Abraham increases the time.
Yeah, it changes the delta t. Yeah, yeah. Can I scroll down? Yeah. So look, you have two situations. So there's one of those big lorries that you see on the road. I don't know how many wheels. Let's just say 4 there. What type of mass would this have? Probably be pretty big. 10,000, 10 tons, if it's fully loaded. Or more even, yeah. And then let's say then here's a car of 2,000. Huh? Yeah?
In Europe, trailers can be max 38 tons.
Can they?
Yeah.
Oh, okay. Let's make this 30. So push it up a little bit higher. Yeah. So let's say this car is going. What would be what would be 30 kilometers per hour in meters per second? That'd be 30 over 3600. What's that? 8.3? Yeah, okay. So look, let's say this car is, in Ireland, the slowest limit is 30. You see them like near schools, okay? So This is outside a school, and maybe it's going at 8 meters per second, which is slightly under the speed limit. Okay. Now let's make this truck go quite slow. Maybe it's at rest and it's only just moving. So with 1 meter a second, how fast would that be? That'd be like, that's kind of fast. Let's say it's going 1/4 of a meter per second. It's just moving, just about. So that's pretty slow, right? 25 centimeters per second. It means the truck is moving like this. It's pretty slow. And here's you. And here you are again. No, this can't be you twice. That'd be bad luck. One of your classmates then. Okay. Let's calculate the impulse imparted onto you by the truck. Okay, so what type of impulse are we talking about here for the truck? So the impulse of the truck, oh, sorry, I don't mean the impulse, sorry, I mean the momentum. The momentum of the truck, that would be this multiplied by this, isn't it? So that's 7,500 kilogram meters per second. And then what's the momentum of the car? 16, isn't it? 16,000 kilogram meters per second. Okay, so in this situation, which is worse to be hit by? The car. Okay, but remember the truck is going really, really, really slow. Make the truck go a little bit faster. Let's say even 1 meter per second, which is still not fast. What's the momentum of the truck here? 30,000. That's over twice the momentum of the car. So when the truck starts at rest and begins to move, very quickly it will reach a dangerous speed. For the truck, we'll say maybe around about 0.5 meter per second. That's when it'll have the same momentum as the car. Obviously being hit by the car at this speed would be quite dangerous. Okay, for the truck it's only 0.5 meter per second. So this is what I mean, the impulse or the momentum is what hurts. It's not the speed or the mass, but the product of the speed and the mass. Okay. Also, the truck has a second problem too. Usually the front of the truck, I think, is much more solid than the front of the car.
And it's usually flat.
And it's usually flat, whereas at least with the car you could potentially roll over it. Not so with the truck. Okay. Okay. Here's another example. So this time what you have is a nail, a 100-gram nail, and you hit the nail with a hammer with 50 newtons. So into the board it goes. Okay. The velocity is 4 meters per second. So you hit this and you make it move with 4 meters per second. And my question is, how long was the force applied? So what's the T? See if you can try this. I think you have to use the formula. You might have to use more than one formula. See what you can do. Yeah, you got an answer. Which formula would you need? You have a few formulas. You have F equals delta P over delta T. You have I equals delta P, and you have I equals FT. So, and you also have F equals MA, I suppose. I think we need to use this one. The F is 50. The M is 0.1, the V is 4, and of course the nail was at rest at the beginning. Nails don't usually move before you hit them with the hammer, unless you drop it. That's 0. Oh, good. So I'm looking for the t. So what do you get for the t here?
8 times 10 to the negative 3.
So it's 8 milliseconds. 10 to the minus 3? Yeah. Which seems right, doesn't it? Like if you have a nail and you strike it with the hammer, the time the force is active is quite small. Right? I mean, you don't push the nail in with the hammer, you strike it for a brief moment. You were thinking about how to hammer a nail, is it? Or yeah? This is your first or second class of the day,
Second.
which I have this morning, maths, was it? Yeah.
Well, actually third, if you've gone hours of class.
Oh yeah, okay. Second subject. Yeah. What are you doing in maths today? The graph? Yeah. Anything else? No? Right. Continue? Right. A 250-gram football is at rest. A football player kicks the ball and the ball moves at a speed of 10. What is the impulse? Okay, we can do this together. What formula could we use for impulse here? mv minus mu, isn't it? What's the u? 0. The v is 10. And the m? 0.25. Yeah. So, what's the I? Well, you can nearly do this in your head. It's going to be 2.5. Isn't it? 2.5. Yeah. The player's foot is in contact with the ball for 100 milliseconds. What is the force? So which formula do you need now? You could use F equals delta P over delta T. Do you know the F? No. Do you know the delta P? Yeah, what's the delta P? 2.5. And the delta T? What's the delta T? Yeah, 0.1. Okay, give me the F now. Again, you could probably do this in your head. 2.5 divided by 0.1 is 25 newtons. Yeah, it's okay? 25 newtons is the answer. Regina, is this okay? Are you sure? You're telling me the truth? Okay, good. Right. These are easy examples, but now it's going to get a little bit harder. Okay. The biggest advantage to using this formula is it allows you to calculate the force provided by rockets. Think about the hot gas coming out of a rocket. It has a mass m and a velocity v, but the gas was at rest. Therefore, its momentum changed. Combine this with Newton's third law, we can get a nice little formula, which I'm going to talk about now. No, don't worry about that. That's just a picture to look cool. Right. So, let's together we'll look at this in detail together. So, here's our rocket, and obviously full of gas, like so. And this gas is at rest, so the U equals 0. Okay. And then what happens is the gas comes out. Obviously, it's very hot when it comes out, but the gas is coming out then. And we could say, maybe we could say delta M per second. Every second delta M comes out of gas. Whatever, maybe it's 100 kilograms per second. The gas is coming out, okay? And not only that, it comes out with a speed, which is obviously not 0. It's usually quite fast, okay? So if you were to look at the gas, how does the momentum of the gas change? Let's keep the up positive and the down negative. So first we have mv minus mu. The m, if we're only looking at it for 1 second, the m is delta m, whatever number that is. And the v, we don't know, it's down though. So maybe I should call this a minus v to show that it's down. And what's the mu here? minus 0. So that's minus delta M times V. Okay? Now that's how fast the gas comes out. But according to Newton's, so this is from Newton's second law, but according to Newton's third law, for every action there's an equal and opposite reaction. So there's actually a reaction here from the rocket. The gas leaving down causes a up reaction onto the rocket. And because of Newton's third law, this should equal this, but just opposite in direction. So this up force, which I'm going to call T for thrust, should equal delta M times V. Or if you want, it's the mass of the gas per second multiplied by the speed of the gas. So it's a very simple formula. Just to give you a number example, so let's say you have your rocket here, and let's say per second we lose 100 kilograms per second, and let's say the speed down is, let's say, 100 meters per second, then the force, thrust force up for the rocket would be 10,000 newtons. The force upwards, okay? So it's actually a very simple formula. Mass multiplied by speed of the gas can give you what's called the thrust force.
The change in mass.
Yeah, the change in mass, or the rate at which you're losing mass. So if you want to call it delta M, you can do that. Yeah. You don't really need the proof. Not that it's much of a proof, but you definitely need the formula. And I don't think this formula is in that formula sheet. So if you can make some notes now on this. This is the key part here. This has gone a little bit messy. Say again?
No.
That's a little example.
How would you define thrust?
It's like the driving force. It's the force of the propulsion. Do you know this word propulsion?
Yeah.
But it's not the resultant, because the resultant we have
It's not the resultant, yeah, because what else is there?
mg.
And something else important too for rockets, the friction. Yeah.
The force of the propulsion, you said.
That's one decent definition of it, yeah. No, actually, to be a little bit more clear on the grammar, you could say it's the force provided by the propulsion. So what's French for propulsion? La propulsion? Or,
La propulsion.
close enough, yeah. It's basically the same.
And in Spanish it's also the same.
Yeah. Okie dokie, yeah. Yeah, we're okay with this. Yeah, sure. What's really nice about this formula is you don't have to use gas. It also works if you use liquid. There's a YouTube video of somebody who built a liquid backpack. Water shoots out of the backpack and they move upwards. I don't know if you've seen this.
Oh, they use it for like they connect that tube to a
Fire hydrant or something like this.
or
Yeah.
like a jet ski, and you just kind of.
Oh yeah, the jet ski. That's right. Yeah, yeah. So it works for gas, liquid too. Okay. You got that? Yeah? Okay. Here's a very simple one for you to try. At launch of a rocket, the gas has a speed of 4462 and 7,485 kilograms of gas is burned and ejected per second. What's the force? Alright, so tell me that. You can multiply and give me the force here.
53,398,070 newtons.
Yeah, so that's a lot of thrust then. Yeah, is okay? Yeah. Right, one last example. Now, this example, I've seen it in the exam before as a section B question a while ago. So, it's a windy day. A physics student is walking home. The student stops for a moment to calculate the force he is feeling from the wind. The wind is blowing at a speed of 12 and the student is at rest. The student is 1.6 tall and 40 centimetres wide. The density of air is 1 kilogram per metre cubed. What is the force felt by the physics student? Let me draw that for you. We'll work at it together. So this is the problem. Here is your physics student. Now I know it looks like a rectangle, but it's actually a physics student. Rectangles are easier to work with. So the physics student is 0.4 meters wide and 1.6 meters tall. Okay? You have a wind blowing here, and the wind blows at 12 meters per second. Oops. And the density of the wind is roughly 1 kilogram per meter cubed. Okay? And that's all the info. And that's enough to calculate the force from the wind. Let's look at it. So here's the trick for these problems, okay? You need to imagine you're looking at just one, I'll put it in green, 1 second of time. Because all of these calculations involving change of momentum are always per second. You know, the change of mass times velocity per second. The change of momentum per second. You know, it's always per second. Okay? So we can just look at 1 second. See what happens in 1 second. If you're only looking at 1 second, it means all you really care about, well, maybe someone could tell me, all you really care about is what distance here. You only really care about what's in front of the student, a distance of 1 second, which in meters is 12 meters. Because if you think about it, the wind that's here will have no effect on the student yet. Only the air in here is going to hit the student, right? The air here is not going to hit him, and obviously the air behind him is not going to hit him. It's only the air right in front of him that's going to hit him if he's walking into the wind. Okay? So, what I want to do is calculate what's the mass of the air here. Right, so what is the formula for mass? Because density is mass over volume. So, mass is density times volume, which in this case will be 1 times 1.6 times 0.4 times 12. What's that, please? 7.68 kilograms. Now, what happens to this air? Initially, it's moving, and then when it hits them, it's not moving. Can you picture that? Here's the air. The air is moving towards him. Look at me. The air is moving towards him, and then it stops when it hits him. So the air has a change in momentum from the air. It's mv minus mu, but the v is 0. So that's minus m, which is 7.68. And the u, now in this picture, it's heading to the left, so it's minus 12 technically. What's that?
Negative 92.16.
So positive, yeah, 92,
Oh, negative times negative.
yeah, 92.16. So, again, according to Newton's third law, this change in momentum, this action, has a reaction. That because his body made the air stop, because his body caused the air to have this change in momentum, then he will feel this momentum too. You know, it's just like action, reaction, okay? I didn't perhaps make this clearer, but if you look here, this is at rest, right? If I hit this, I give it momentum. Yes? The momentum that it gets from me, I feel that as a negative. Okay, so if I give this 1 kilogram meter per second of momentum, then there's a minus 1 kilogram meter per second in my hand. This again is Newton's third law. So, this air gained momentum, so then the student, it will have an equal and opposite, minus 92.16. Oh, sorry, I wrote Newton's here, I'm sorry. Kilogram meters per second. Kilogram meters per second. Right, so finally, what's the force on the student? So we can use F equals delta P over delta T. The delta P is minus 92.16 and the delta T, 1, good. Why is it minus for the student? Yeah. If you're walking into the wind, you will feel a force this way, won't you? 92.16. Yeah? I know this is a little bit tricky, but it's a good example of using momentum and impulse and Newton's second law and Newton's third law.
So what is the question?
Huh?
What is the question?
We can flick back to it. Guys, before you write this down, what would happen if, as the student was walking, they make their height smaller? So if they kind of bend over so that their height is, let's say, 1 meter, or 0.8 meters, we'll say. What would happen to the F? Would it be bigger or smaller?
Smaller
How much smaller?
by half.
By half, because in the calculation, which number changes? This number is half. So this number is half. And all the way down, this number is halved. Yeah? So this is why it's easier to walk when you hunch down. Because when you're walking in the wind, if you stand upright, you have all this area. Whereas if you're leaning forward, you've reduced your area.
Which is like the head of the letter.
Yeah, you want to reduce the area at the front. Yeah.
Walk sideways.
Walking sideways too? That would
Shuffle.
shuffle along. You've only got this much area exposed. Yes? Unless you have a big beer belly, and then it might be better to face forwards. So this is a section B question, like I said. It's a little bit tricky, okay? So once you carefully write that down, then I can flick back to the question if you want to copy it. What are you doing?
I checked the rugby score.
Who's playing?
South Africa versus Canada.
Oh my.
40-0 at half-time.
South Africa and Canada.
Yeah.
Half time. So it could end up being 80-0.
Yeah, well, New Zealand beat them 63-0.
Harsh. Harsh. anybody's country playing in rugby?
Yeah, South Africa.
Yeah? And your home country is?
Spain, but we are good at rugby 7, not at rugby union. So,
Are they in this?
no.
No. South Africa is obviously. Any Asian countries? Japan is one. Japan's doing alright.
Yeah.
Yeah.
Japan's doing alright. Actually, it's doing better.
They beat Ireland.
Yes, yeah. Afterwards, I was looking up the explanation. Apparently, the Irish team didn't cope so well with the heat. It was
And
what
they fielded,
sauna conditions, they described it as.
they fielded the B team as well. They were overconfident.
Oh, that's cocky.
Yeah.
That's cocky. Yeah. No, well, I'm happy for Japan because they're hosting it, you know. So they're at the top of the group at the moment, aren't they?
I think so.
I think they are, yeah. Any other Asian teams in the?
Well, Georgia. It's Georgia's in Asia. East Asia.
Yeah. Nobody else?
Who?
Georgia.
Georgia.
Between Europe and Asia.
Yeah.
Good
No,
side.
no. No Chinese rugby team, right?
No, still don't get it.
No.
What sport is it?
Huh?
But it's
Rugby.
rugby.
Rugby's not popular in China.
Yeah.
Yeah. Basketball is popular in China.
No, NBA just got banned in China.
Did it?
Yeah.
Really?
Yeah.
Too American? What's the reason?
No, the reason is the racket manager.
Yeah.
He agreed to protest in Hong Kong.
Oh,
Make a tweet.
it's Hong Kong reason.
Yeah.
Okay. So no more NBA.
Just make a disagreement. It's
Okay.
not like a ban. I don't think it's gonna ban forever.
Yeah, because it's too popular.
Yeah.
It's too popular. Right. You needed to write something down from the question, maybe. So the student feels the force backwards. So I suppose the student must put some force forward, otherwise they'll fall down. You know? How much force? The same. What is it? 92 newtons, isn't it? So if they want to begin walking, they would need it at least a little bit more. Okay, so what we'll do, we'll have a second lesson in a couple of minutes. Yeah, we'll just take 5 or so minutes. What's the next topic coming up anyways? Oh, easy peasy. Good, okay. So yeah, this one was a little bit hard, but the next lesson is quite easy. Can you try the homework for a few minutes and then we'll start the next lesson. We'll get 2 topics today. What?
So
How many questions? Hundreds? Thousands?
16 or something.
18 questions.
What does that tell you then for the exam?
That there is a lot.
It comes with a lot, yes.
Oh,
Alright, we have class tomorrow, don't we?
Yeah, but
Yes.
it's split. But we have someone is coming to talk.
Okay.
So we
Now
have
what I
to
mean
talk
is,
to
why don't you try to do all the even questions for tomorrow? So you could do 2, 4, 6, 8, 10, 12, etc., etc. Yeah, 9 questions then. Because I don't think there'll be much in the second lesson because it's so easy. So it'll mostly just be these questions tonight, okay? Can I close this now?
just
Yeah.
So our final chapter is
Sport,
about
just
the
trying
right?
to do 2 minutes.
Yeah.
So it's ending for the first semester or the second semester.
Say again?
So it's ending
Yeah.
at the first semester.
No, Atoms is for the second semester.
Oh,
It's the
okay.
very last.
Oh, okay.
Okay, are you trying that now?